Yesterday our lesson was on solving. We never called it this yesterday, Garrett. We didn't call it this yesterday, but it's yesterday we were looking at 2x2 systems of equations, and today we're going to be solving 3x3 systems of equations. You did this in Algebra 2. You probably did it over a course of 3 or 4 days. We're going to cover it in one day, just kind of review it. We're not going to do any matrix techniques. We're not going to do any Cramer's rule. We're not going to do any Gaussian elimination. I'll save that for your linear algebra classes in college. We're just going to use algebraic elimination to solve 3x3 systems of equations. Now, what do we mean? Yesterday was 2x2 systems. Today is 3x3 systems of equations. What do we mean by 3x3 system of equations? Three different equations with three different variables. That's right. A 2x2 equation has two equations with two variables. Now, what we did in class yesterday, right? 2x2 systems of equations are a linear. We looked at linear equations. Ax plus by equals c, standard form of a linear equation. 3x3 systems of equations look like this. Three different equations with three different variables. What kind of equations are these? X plus y plus z equals 6. What kind of equation is that? It's easy for us to talk about what kind of equation, say, 2x plus 3y equals 6 is, right? It's a linear equation. We can talk about the slope. We can talk about x-intercept. We can talk about y-intercept. We can talk about graph. You know, a lot of different things we can talk about with 2x plus 3y equals 6. But you guys are used to working with these 3x3s. You did it extensively in Algebra 2. But what is it? Any idea? X plus y plus z equals 6. What if I told you it was just a linear equation in a three-dimensional space? Could you buy that? Can you picture what a three-dimensional space might look like? Could we have an x-axis? I know that's kind of slanted, but it looks better this way. And could we have a y-axis? Here's an x-axis, here's a y-axis. And slicing right through vertically, we have a z-axis. Okay, so you can kind of see a little bit of a three-dimensionality taking place there. We have a three-dimensional space with an x-axis, a y-axis, and a z-axis. Okay, and these equations, x plus y plus z, is the set of all x, y, z points that add up to be 6. Here's an example of a point that's on that line. X is 2, y is 0, z is 4. Agreed? X is 5, y is 1, z is 0. Okay? And all of those points, if we graphed it, if we went over to where x is 5 and y is 0, 1, 2, 3, 4, 5, and z is 1, we're going to come up right there kind of in space, and there's the point. Right? Right. We don't really have right, left, and up. You know, it's kind of weird because the axes there's 6 directions we're dealing with instead of just left and right, up and down. We have left and right, up and down, and then another left or right, forward or backwards if you speak, right? So you can kind of picture what the three-dimensional space was like. But all of the ordered triples, not ordered pairs, ordered triples that make that equation true would form a line in a three-dimensional space. Okay? So we've got these 3 lines in a three-dimensional space. And what we're trying to do is find the point of intersection of all 3 of those lines. What is the ordered triple, if there is one, that all 3 of those lines pass through? All right, now I'll give you one more little bit of theory. I'm going to hold these things up kind of. I need a third hand here. So. X-axis, Y-axis. right, flat, z-axis, right? And then we've got these lines just out here in space, right? They may cross the axis, they may not, okay? These lines are out here in space. So they're just three-dimensional lines. Now think about how many different ways lines in three-dimensional space cannot intersect. Because if they're not parallel lines, because parallel lines by definition for geometry have to be in the same plane. They have to be in the same flat space. But if we go out of a flat space into a three-dimensional space, there's all kind of scenarios where lines won't intersect. So if we talk about in a three-dimensional space, having three lines that all intersect in a single point, you have to make it work. Because there's so many different ways in the three-dimensional space that lines won't cross. But to have all three lines crossing in a single place, one point, they all intersect together, that's kind of really a rarity. It wouldn't happen just if you tossed three lines at random into a three-dimensional space. They're probably not going to all intersect in one point. So just a little bit to think about what we're actually doing that you haven't thought about before. When you take that class that I was talking about in college called linear algebra, you'll do a lot of three-dimensional type thinking. Here's what it looks like. Can any of y'all think of a scenario in real life that has three variables? There is a fourth dimension. Time. So if you actually put something into motion in a three-dimensional space, then you have a fourth parameter acting on it. So that fourth dimension is considered to be time. Like, I don't know if you guys are, when ladies go get ultrasounds for their pregnancies now, they do a 4D ultrasound. It's four-dimensional. Because it has depth and it has three dimensionals physically, and then it's actually in motion, so the fourth dimension is time. So there is a fourth dimension in the physical universe. All right. If you look at something that's not in motion, then there's three dimensions. But if something's in motion or actually moving, playing out over time, then there's a fourth dimension. So multivariable scenarios happen all the time. Okay, just a perfect example. Car dealership. Cars, you have trucks, you have SUVs. And there's other categories, but that's a three-parameter scenario, X, Y, and Z, where we could talk about what each of those parameters is doing in time. You could graph it, you can look at it together. It may not be linear, the relationship with sales that's going on with those three things, but there's three-dimensional. You could have four-dimensional. You could have lots of multivariable situations that come into play. Okay, so just kind of think about what we're looking at and what it could possibly apply to. All right? Now, how would you solve this? What do you remember? Do what? 4 squares. 4 squares. Oh, okay. Now maybe you're talking about 4 matrices, right? You have or 3 matrices. You have the 3 matrices, and then the determinant is the fourth one, and the fourth one goes on the bottom. So you're talking about Cramer's rule. That's good memory. We're not going to do any matrices techniques, but your 4 different values, that's great. There's 3 coefficient matrices, or 3 numerator matrices, and a 4th one that goes in every denominator. That's a good recollection. We're not using that technique. We're going to use elimination. All right, so let's just dive into it. The first thing we're going to do is look for a variable that we can easily eliminate. Do you see a variable that we could easily eliminate? Z can be easily eliminated, right? We can add equation 1 and equation 2 together. Right? We can take x plus y plus z equals 6 and 2x plus 3y minus z. And you wouldn't have to rewrite this off to the side. I'm just doing it. So you could just add 1 plus 2. And what do you get when you add those 2 equations together?
3x plus 4y.
3x plus 4y equals 11. Z is gone. All right? The next step is to pick 2 different equations and eliminate z again. All right, we're just going to keep this equation, 3x plus 4y equals 11. We're going to keep that equation. You can actually put a box around it, something to, because you can get lost. There's a lot of work that's going on here. You could kind of lose things if you're not careful. 3x plus 4y equals 11. Now, we've eliminated z. We need to eliminate z again using two different equations. All right, so which two equations could we use to eliminate z again? The bottom two works. You could use the first one and the third one, but you'd have to multiply by a negative, and that's a little bit more clumsy than doing that. So if we take the bottom two, and if I multiply the second equation by 2, that gives me, and you don't have to show all these steps, you could just come over here and show this one step. Multiply this by 2, and that's going to take you to that, right? 4x plus 6y minus 2z equals 10. And if we add those two equations together, what do we get? Are y'all with me? Bad day to daydream. 7x plus 2y equals 11. All right, so that's our second equation that we're going to use. That's of importance, right? So now I have created, using these equations, I've created two equations with two variables, and I can go back to my techniques from yesterday, my 2x2 techniques, and solve that system of equations that results. So these two equations that we have left over here, 3x plus 4y equals 11, and 7x plus 2y equals 11. And we can solve those using a 2x2 technique. Suggestions? Eliminate the y's by multiplying the bottom equation by -2. All right, multiply the bottom equation by -2. That gives us that. And pretty quickly, we get -11x equals -11. Divide both sides by -11, and we get x equals 1. Right? Y'all with me? I know I'm going kind of fast. You catching up? I like your trees there. It's pretty. X equals 1. Now, what am I going to do with x equals 1? Plug it into one of these equations, right, with two variables, and find y. So if I plug it into one of these, let's take the first one there. If you plug 1 in for x, you get 3 plus 4y equals 11. Subtract 3 from both sides, you get 4y equals 8. Divide both sides by 4, you get y equals 2. X equals 1. Y equals 2. What do I need to find? Z. Well, using that very first equation that we're given, right? X plus y plus z equals 6. Right, we have 1 plus 2 plus z equals 6. 1 plus 2 plus z equals 6 means 3 plus z equals 6 means z equals 3. So our solution here is, how would I write the solution? How would I write the solution? 1, 2, 3. It's an ordered triple. What is 1, 2, 3? It's the point in the three-dimensional space where these three lines all intersect. Okay. Now, if you ended up with three lines that didn't intersect, you're going to end up with some contradiction somewhere, or we won't be able to eliminate variables the way you need to eliminate variables. Okay, you get inconsistencies, and that's going to tell you that there isn't a common intersection for the three lines. But I'm not going to go that far with this skill. We're trying to finish up and get through this, so we're just going to kind of look at it. All right, y'all good with that?
Yeah.
All right, next example. Let's walk through this one. Go ahead and write it down. 2x plus y plus 3z equals 8. X plus 3y minus z equals -6. 3x minus y plus 2z equals 2. Now, do any of you guys have the newest TI calculator, TI-84? color edition? Not with you? See if it has a 3D graphing mode. Just check and see. See if it. See. They make some. The TI-92, an older version, actually had some pretty nice 3D graphing. You could look at three-dimensional curves and three-dimensional graphs. It's kind of interesting to see it. If you can see it, it's better. We got 2x plus y plus 3z equals 8. These three linear equations in 3 dimensions. All right? Do you see something that eliminates easily? The y is the easiest variable to eliminate. Kind of always jump on that one and use that one to eliminate it first. So if we eliminate the y by adding the first equation and the third equation together, what will we get? First equation plus the third equation gets us what? 5x plus 5z equals 10. That's correct. All right? We're going to save that one for use in a minute. Now I need to eliminate, because I've eliminated y, I need to eliminate y again using 2 different equations. Which 2 seem to be the most likely candidates? The bottom 2, right? Because I can just multiply the bottom equation by 3. So we can multiply that bottom equation by 3. I don't like the way this PowerPoint animates this because there's too many steps. If I multiply the bottom equation by 3, what do I get? 9x minus 3y plus 6z equals 6. And then this equation is x plus 3y minus z equals negative 6. Be really careful doing too much mental work on these 3x3s. There's just a lot of steps, a lot of ways for things to get lost. And then if we do that addition, we get 10x. These are gone. Plus 5z equals 0, the hero. Okay? Take a walk. So the 2 equations we're working with are 5x plus 5z equals 10 and 10x plus 5z equals 0. I'm running low. Is everybody okay with that? Now what can we do? Multiply one of the 2 by a negative 1. Change all the signs. I'm out of Germ-X, buddy. I'm out of Kleenex. This is a very not clean room at the moment. All right, so we can change one of the, it doesn't matter which one. I probably would have done the top one, but this PowerPoint uses the bottom one. And then we get x equals negative 2. Right? Ye. X is negative 2. Substitute that in for x. Solve. And you get z equals 4. Now we just have to find which variable. Which variable is missing at this point? Y is missing, right? So we need to go back to one of our original equations that has x, y, and z. Doesn't matter which one you use. This one uses the first equation, but any equation that you use is going to work for you. Make your substitutions. Negative 2 is x. 4 is y. 4 is z. That's a mistake you can easily make, right? Substituting for the wrong variables. Make sure you're making the right substitution, correct substitution. And we end up getting y equals 0. All right? Now, how would we express this answer? Negative 2, 0, 4. It has to be ordered alphabetically. X, Y, and then Z. There's a real temptation here to put the variables down in the order that you solved for them. So you got to be careful for that, right? Make sure that your ordered triple is X, Y, Z. If the system of equations had A, B, and C, then the A value comes first, the B value comes next, the C value comes third. It's always ordered that way. All right? One more example and one exception, and then we'll kind of be done. So try this one on your own, and we'll continue in just a second. Once you add the first two equations to eliminate y, you have to pick two more equations to eliminate y. And most people that I've looked at chose to use the second equation and the third equation and multiply the second equation by 3. All right? Which gives you that. 3x minus 3y plus 12z equals 18. X plus 3y minus 4z equals -2. So when you add those two equations together, you get 4x plus 8z equals 16. Did you add incorrectly?
Yes, sir.
12 minus 4 is 8.
Put
Yeah,
6.
like so. Yeah, the problem is all these little arithmetic operations. If you make one little arithmetic error somewhere, it's just the process is just shot. You change the linear equation, right? And you're most likely not going to get an answer. Okay, not one that's going to check out anyway. So the two equations we're working with are 2x plus 6z equals 9. 4x minus 8z equals 16. All right, what are we going to do next? Eliminate the x. Now, you can do that by multiplying the top equation by -2 or dividing the bottom equation by -2. All right, it's most kind of natural, organic to multiply than divide. And when you do that, you end up getting z equals 1/2. Everybody get there? Peyton, you good? Now we want to make one of those substitutions or make that substitution in one of these two equations. And that's going to give us 2x plus 3 equals 9, x equals 3. All right, now from there, we're going to make a substitution back into one of our original equations. X plus y plus 2z equals 3. Substitute 3 for x, 1/2 for z. And we're going to get y equals -1. All right. This is why we have to operate with a very high level of efficiency with our integer operations and arithmetic. If our arithmetic is sloppy, we mess up these processes. It's hard to work through one of these problems because there's probably 50 arithmetic operations in a problem like this that you're having to do. Multiplication, addition, it's a lot. So even if you're 95% efficient with arithmetic, good chance of missing a problem like this. Need to be 100%, 100, right? All right, last problem. We're not going to actually work this one. What's different about this problem? What do you see right off? Talking about eliminating variables. See anything, Jagger?
X,
What about x?
like you did, doesn't have any number in front of it, like that.
Right? What about the y's? So, see what's different on this problem, and if you see it, then you save yourself some time. We could use those two equations to eliminate x and y in one step and get us straight to a z value. Right? And what it would look like is this. Yes?
Take Pinion's checking out after this class period.
Okay.
Thank you.
So you can change the signs in one of those equations And when you add it together, you get 3z equals negative 12. Z equals negative 4. And what can you do with that, though? We still need to find x and y, right? So what you can do, here's your options. You can take z equals negative 4 and you can plug it into these other two equations in the place of z. And then we just have x and y left in those two equations, right? But you could also take these two equations down at the bottom, come right here, subtract those two equations, subtract that one. If you add those two together, now what do you get? Negative 3y minus 5z equals 17. Plug the z in right there and solve for y. Yep. So there's lots of options that you have. It's not always going to follow this same, get two equations and two variables. Sometimes you can eliminate two variables and jump straight to one of your numerical solutions and then substitute from there. All right, so just kind of a dance with who brung you scenario. All right, homework is these 4 problems. Take a screenshot of that. Make sure you get the answers at the bottom so you can check your solutions.